Thank you. So hi everyone, I'd like to thank the organizer for inviting me. It's a very pleasure to be here and to present our work. So today I'm going to talk about scanning tunneling microscopy we've been doing on rhombohedral trilayer graphene, where we were visualizing intervalley coherent states in three different ways, in spectroscopy, in real space, and in momentum space. So that will be the first part of the talk. And at the end, I'll show you some more recent result where we measured also one-dimensional strain-induced ABC structure, and we'll see the effect of strain on this one-dimensional structure and how it modified the band structure and gives rise to correlation effects even without the application of displacement field. Okay, so let me introduce first the people that actually did the work. So this work is a collaboration with the group of Andrea Young in Santa Barbara. They fabricated the sample, Young June, and we measured in the Weizmann Institute. The measurements were done by Ivan Leo and Ambikesh Gupta. Ivan is our postdoc, very talented postdoc, and Ambikesh just finished his PhD in moving to Washington University. And theoretical support by Yair Vituri and Erez Berg. And for the second part, we collaborated with Paco is sitting here, Pierre, Zen, and Adrian. This is a work in progress, so I'll show you the result and qualitative understanding. Let's begin. So the outline will be as follows. I'll give some short introduction to rhombohedral trilayer graphene. I'll show you how we perform gate-tunable spectroscopy, and then I'll show you the visualization of intervalley coherent states in spectroscopy, in real space, and in momentum space. And in the last part, I'll show some strain-induced topological and correlated states on 1D ABC graphene. So rhombohedral graphene, so maybe I don't need to introduce. So the natural stacking of graphite is ABA, but 10% grows as rhombohedral, where every layer is shifted by a third of a unit cell with respect to the other layer. And when this is created, this can stay for a long time, especially if you isolate the pure ABC region, then it will stay for a long time as a metastable state. And then the dispersion behave like a parallel, where n is the number of layer. We have attaching, which becomes flatter and flatter as we increase the number of layers, starting from a Dirac, which characterize the monolayer, and then it becomes flatter and flatter. The band structure is determined mostly by the orbital at the end of this SSH-like chain. And indeed, this very flat region gives rise to very sharp van Hove singularity, which one of the nice things is that they can be tuned very easily by the application of displacement field. And indeed, this is the band structure of different, of course, there are the details of the specific system with the number of layers, and there were many correlated phases that were observed in a different system with different number of layers. So now let's focus on the three-layer, the trilayer graphene. So this is the crystal structure. Again, 3 layers shifted by a third of a unit cell. This is the Brilliant zone with the K and the spin degrees of freedom. And then at every valley we have this single particle band structure, which consists of 3 pockets at low n, which merge at a saddle point via van Hove singularity to an anomalous Fermi surface, and then it change to a simple Fermi surface which is trigonally warped. And if we take a cut through one of the C3 symmetric axis, we get this band structure where we have this touching point without the application of displacement field, and when we apply displacement field, it opens a gap which becomes larger and larger as we increase the displacement field. Already without displacement field we have this Van Hove singularity, but when we apply the displacement field, the band edges becomes flatter and flatter, and the Van Hove singularity becomes sharper and sharper, so we have huge, very high density of state, and the name of the game now is to bring the Fermi energy to this very sharp Van Hove singularity and to look for a correlated state. Okay, so indeed this is an inverse compressibility measurement that was done by Andrea. So, and this is the phase diagram that one gets when we bring the Van Hove the Fermi energy into the Van Hove singularity. So here you see still the four-fold symmetric phases, the single particle phases, the three pockets that merge into an annulus and to a simple Fermi surface. However, here in between we see the symmetry broken phases, similar to what observed in twisted bilayer graphene, a cascade of symmetry broken phases. Here is the half metallic phase where the spin is polarized and the valley is unpolarized. We get it with the simple Fermi surface and with the annulus, and then the quarter metal where both spin and valley are polarized. And this can be explained, as Erez explained yesterday, by the Stoner instability, a flavor cascade, which take into account the single particle density of states, exchange interaction, which wants to gain exchange energy by polarizing the electrons, and then the Hund's coupling that determines which flavor will be the actual one. Okay, now when you cool the system to low temperature, you get this superconducting pocket with, these are the TC of 100 millikelvin and 50 millikelvin. SC1 is probably a spin singlet. This is, you see that these pockets are adjusted to the symmetry broken phases, so the SC1 is adjusted to the normal phase, probably a spin singlet, and SC2 is adjacent to the ferromagnetic phases and is believed to be a spin triplet. However, as we heard yesterday, the whole day, the underlying mechanism for superconductivity is not yet understood. There are several proposals: spin fluctuation, IVC fluctuation, Magnon fluctuation, as described yesterday by Andre. So, and one of the proposals that were done by Erez and Yair is IVC fluctuation, and it was our motivation to really see whether IVC states exist in this phase diagram. Wanted to use the advantages of FTM as a real space and momentum space tool to be able to look for intervalley coherent phases. So, as we said, one of the way to minimize the energy is to form intervalley coherent phase. In this states, the wave function form a coherent superposition between the k and the k prime. Instead of polarizing the isospin in the k or the k valley, we actually count the spin in one direction, breaking the U1 symmetry, and gaining exchange interaction with a minimal cost of kinetic energy due to this momentum-dependent valley splitting, which is generated by this trigonal warping. We actually think of it as these two annulus fold one on top of another. And experimentally, having an STM, what we want to look for is this folding and hybridization should give rise to a band splitting, which we can look in the density of state. It also gives rise to band reconstruction that gives rise to new scattering channel that we can, in principle, look for, detect with the quasi-particle interference method. And then this superposition in momentum space is expected to give rise to charge density wave with the specific k vector, k minus k prime, which is known as the Kakula CDW that were observed in other systems. Okay, now this phase diagram was measured with in a device where the trilayer graphene was encapsulated with a dual gate, top and bottom gate. Having an STM, we should get rid of the top gate in order to be able to come with the tip and measure. So we have only one gate. This means that we cannot change the carrier density and the displacement field independently. So we cannot probe this whole phase diagram. What we actually do when we change the gate voltage of this bottom gate, we change both the carrier density and the displacement field. So we actually take a linear line across this phase diagram, and we need to hope that we will be lucky that it will cross the actually interesting stuff. We can change the location of this line by for example, dipping the tip into, because this is determined by the capacitance, by the different capacitance, and by the work function difference between the tips. So we have some control on it, but in principle, this is where we go when we do STM measurement. Okay, so this is the actual image of the device. And this is the device geometry. We use a capacitance navigation using this electrode in order to get and to find the sample, and then at the end we jump on the sample. So this is the geometry, silicon dioxide substrate, on top of it graphite baked, HBN, and then the bilayer and monolayer. This is actually the rhombohedral trilayer, and in a minute we'll see why we draw it like this. Okay, so a few words on how we create this rhombohedral trilayer graphene. So we do it by the twist method. We take a bilayer graphene, and then we put a monolayer, and we twist it by a tiny angle, and this gives rise to different regions of ABC stacking, ABA and ABB stacking. This is the most stable configuration. This is the least stable configuration. So after relaxation, this shrinks into very small region, and then we get, assuming there is no strain at all, we get this very isotropic triangle with ABC and ABA region. If there is a tiny strain, then we get this elongated. However, we did a very thorough strain analysis, and we found out that actually inside this triangle, the sample is free of strain. It relaxes very rapidly, and it concentrates on these edges. And at the end, I'll get back, and we'll see actually the effect of strain on these one-dimensional channels. Okay, so now let's start to see some data. So this is a topographic image of such a region of the sample. Here we see very faintly a triangle, which is the ABC structure. And what we found out just at the beginning, we can actually change and control the shape of this ABC region by the aid of the STM tip. You can see that in the second image, it just disappeared. And then when we apply displacement field and continue scanning the same region, it reappeared. And then after several scanning, it became stable and didn't change its shape anymore. And this is consistent with an old work by Yankovic and Pablo, where they showed that actually this soliton, this boundary between the ABC and the ABA, can be moved by a van der Waals interaction between the tip and the soliton, and by applying displacement field we actually make the ABC more favorable than they would have been without the application of displacement field. And this is actually the same effect that we see here when we scan under displacement field. Okay, so let's concentrate on this triangle, which was stable from the beginning. This is the ABC, this is the ABA region. Here we see the boundary between the ABC and the ABA. On the left we have the ABC, on the right we have the ABA, and this is the domain wall in between. Let's see some, okay, so this is a zoom in of the crystal structure. We actually see that we don't see the hexagonal structure, but we actually we see only one sublattice, since the other sublattice, the density of state, gets suppressed because of the coupling to the layer below. So what we actually see is the triangular structure of one sublattice. And now let's see some spectra. So this is the IDV measurement. This is the density of state as a function of energy that was measured on the ABC region, and this was measured here outside on the ABA. If we correspond it with the low energy band structure, we can very easily recognize the remote bands that are by this kink of the ABC, and this is the Van Hove singularity of the valence band. We see only one Van Hove singularity due to layer polarization. In a minute we will see how it changes as a function of displacement field, and this is corresponding to the band structure with the linear dispersion of the ABA. On the boundary itself, we see in-gap state, and which we'll come back to at the end of in the other part of the talk. Yeah, sure.
So when we start showing that different observations, different evolution, there were two possible elements. One was before each march into large the annual market structure. And then
No. I'm talking. What I'm showing here is already under displacement field. Here, the under large displacement field, the gap open, and what you see here is the Van Hove singularity of the bottom. It's not the change between the annulus. It's already the bottom of the band, the flatness of the bottom of the band due to the application of displacement field. Right. Yeah, so you will see. Okay, in a minute. Wait a slide, and you will see it. So this is the displacement field that we. This is the spectrum that we see under negative displacement field, and let's see how it changes as a function of displacement field. So here you see this, the IDV, and how it changes as a function of displacement field. So the effect of displacement field has several effects. It opens a gap, and this gap increases as a function of displacement field. It also flattens the bands, and that's why the Van Hove singularity becomes sharper and sharper. And it also changes the localization of the wave function across the layers, so we have layer polarization. So at negative displacement field, we see only the Van Hove singularity of the valence band, and at positive displacement field, we see the Van Hove singularity of the conduction band, and the other Van Hove singularity is on the other side, but we are measuring with STM only from the top. Okay, so, and this is consistent with the tight binding calculation. Okay, so now luckily in this sample the zero displacement field coincide with actual zero displacement field. There is no offset due to some work functions, and this kink is actually the CNP, which we recognize by the change of the slope, which reflects the compressibility, and this in this way we can change the CNP. Okay, so now we want to concentrate on this region. Here we see that the Van Hove singularity is very sharp, very intense, and it also located at the Fermi energy. So this is exactly the condition where we want to look for correlated phenomena. So let's look at it very carefully, more carefully. This is was measured at 4 Kelvin, and now if we reduce the temperature to gain energy resolution, we see that this band actually show a cascade of splittings. So the fourfold band, when it enters, when the Fermi energy, when it starts to fill up, we see splitting. This is exactly what Erez explained yesterday. We have some symmetry broken phases. Here I'm taking the profile, and for example, here you can see that out of the 4 flavors, we see some gets empty, goes above the Fermi energy, and the other parts gets filled. In order to really characterize, we need to do some more measurement, but what we see here is 3 different splitting. So in order to characterize them, we went to the actual conditions and look for what we see spatially. So as we said, we wanted to look for intervally coherent states. So these splitting, in principle, if they are intervally coherent state, they should be accompanied by some charge density wave, and this is what we were trying to look for. So this is an example of a spatial density of state map that was taken at -1 volt, where the Van Hove singularity is not at all at the Fermi energy, and we don't expect to see any effects of correlation. And indeed, when we take a Fourier transform, we see only the Bragg peak of the graphene lattice. And if we do the same at the condition where we see the splitting, we see already that the real space is distorted a bit. And when we take the Fourier transform, we see, in addition to the graphene peaks, we see another set of peaks that are located exactly at the reciprocal lattice divided by square root of 3, where the Kekule Bragg peak are expected to appear. Similarly, we see this at the upper splitting. Here you don't see, like the modulation is even smaller than what we see here. We don't see by eye in real space, but when we take the Fourier transform, again we see these additional Bragg peaks. And if we do the same in the middle splitting, I'm showing here only the Fourier transform, we don't see the additional peak. We see only the graphene, in a similar to what we see here when we don't expect to see any effect of correlation. So we identified this splitting both by the fact that this is symmetric splitting with the half metallic phase, and these are 2 intervally coherent phases that kind of encapsulate the half metallic phase. And this is also consistent with theoretical work by Yahr and Erez, when they show that this is actually what we expect to see. The Kekule is not the Y Kekule or the O Kekule, where the wave function is concentrated on the bond, but actually we see charge density wave where every third site is more intense than the other one. And if we try to take some line cut along this and along here, we expect to see high intensity, low, low, high intensity, and this is this black line where we see high intensity, low, low, and high intensity. So, and later on I'll try to explain why we think that this is not as ordered as expected here in the theoretical. Okay, so what we've seen so far is the following. We see some stoner instability, at least a splitting which is not accompanied by a additional charge density wave, and then the IVCs encapsulating this splitting. And Yair and Erez did the Hartree-Fock calculation, and qualitatively they get the same order with the half metallic phase encapsulated between the intervalley coherent phases. The splitting that they get are an order of magnitude larger than what we get, but qualitatively the picture seems to be with the same order in the phase diagram. Okay, so we found out that we see this splitting in the density of state. They are also accompanied by the Kekule Bragg peaks. And the last way that we wanted to see it is through, we wanted to try whether we can see really the reconstruction of the band structure using quasi-particle interference. So when this folding of this annulus on top of another, as I said, it gives rise to new scattering channels that we were hoping to see using quasi-particle interference. So what we did is the following. So we went to this region. So in quasi-particle interference, just to remind to those that are not familiar with the technique, we measured the density of state around impurities or near stepazers, and these serve as scattering potential to the surface electron, and it gives rise to Friedel oscillation or quasi-particle interference, which reflects the scattering processes on the surface, and this gives information about the band structure, because this scattering happens among the bands in the band structure. So in principle, if we have some interaction induced reconstruction of the band structure, we in principle should be able to see it in quasi-particle interference. So what we did is the following. We did this quasi-particle mapping along this line. This is the location away from, this is where the impurity is located, and this is the energy. And you see these interference pattern, these waves that are shown here. So what we did it at zero displacement field, where the Van Hove singularities are very shallow, so we don't expect to see any effect of interaction. And then we did the same measurement. We did the same measurement at 9.5 volt here, around here, where the Van Hove singularity is at the Fermi energy, and we expect to see, and we wanted to see whether we see some differences that can tell us about momentum reconstruction. So we take the Fourier transform of this, so this is the quasi-particle interference, and we compare it with joint density of state calculation, which is first approximation of this quasi-particle interference, and we can see the valence band and the conduction band, and we can see how it continues, and we see very faint, but still we see the shape of this band. So this is without interaction at zero displacement field. And when we look very carefully around here, we see that these bands actually acquire some splitting when we do the same measurement at 9.5. And if I zoom in, I see that this band actually split into these three different bands. And then we compared it with the Hartree-Fock calculation of the band reconstruction, and we were able to actually quantitatively correspond this scattering vector. This is the data, and below it is the theoretical scattering channel and how that disperses as a function of energy. So altogether, we were able to see also how the band structure is reconstructed due to this interaction. Okay, the last thing we did here is we wanted to look more closely with better resolution on this intervalley coherence phase. So on one of the intervalley phases, we took a larger map, and this allows us to get the intervalley Bragg peaks, but much sharper. And then we found out that they are actually don't fall exactly on the location where the commensurate intervalley coherence peaks should appear. So this means that we have like an incommensurate charge density wave, that they are not commensurate with the crystal structure, but they are deviated, and this can be fit to, again, the theoretical proposal by Erez and Yahr, that they showed that actually in the rhombohedral trilayer graphene there should be crystal phase, which instead of folding these anolos one on top of another, we actually, the scattering vectors that connect them is from this nesting part of this inner pocket and the outer part, and this would give rise to Bragg peaks that are not commensurate with the crystal structure. And this is actually CC symmetric, so this could be actually the phase that we see here in this measurement, where the Bragg peaks are deviating with from the actual location. And this can also explain why this looks disordered, because here we did some simulation where we took like the graphene order, and then the IVC commensurate and incommensurate, and when you merge them together, it looks quite disordered. So this can explain also the disordered real space mapping that we see in our measurement. Okay, so this is the first part of the talk. Questions so far? I'll just summarize this quickly and move to the second part. So we were able to see intervalley coherence phases using scanning tunneling microscopy by splitting of the density of state accompanied by charge density wave, and also reconstruction of the band structure using quasi-particle interference. One of the phases seems to be an incommensurate intervalley coherence phase, and this agrees nicely with Hartree-Fock calculations, except for the size of the splitting. And one comment that I have to say, that, you know, comparing this with the phase diagram that was done in dual gate is questionable. It seems that we see the same order, but according to our measurement, we think that the phases are extended to a lower displacement field, and this is reasonable because we have only one bottom gate, less screening, so it seems that the phases are extended to a lower displacement field, which allowed us actually to see this cascade of phase transition in the condition, in the range of displacement field that we applied. Questions? Yes? Stronger? So here are the superconducting pockets, right? So we, to the, right.
So here, at least in the ABC curve, the whole side goes to the left of the curve where the curve is
Mm-hmm.
yeah, at least in the sense that here, yeah, it's definitely an analysis. I don't know if you can see that. By tiny out of
Guys, we can continue if you want to go, but you decide. You ask for questions.
So how much time do I have? I have 5 minutes, so I'll just okay. So I'll go to the other part, and then I'll start to describe. I don't know how much time I will get to. So anyway, what we looked for so far is a measurement that were done here inside this ABC, where we have actually two-dimensional rhombohedral region, and now I'd like to show you some measurement that we did here on the boundary between ABC and ABA. Actually, this is very nice because in this sample we actually have 3 samples. We were able to measure the ABC, the ABA, and we have also works that we are working with Adi on the ABA. And also on this one-dimensional channel. So as I said at the beginning, if there is no strain, then we get these very isotropic triangles, but a tiny strain can gives rise to a structural transition, and then we get this one-dimensional channel where these triangles become elongated by the ABC region here is not disappear due to structural topological consideration. So we get a situation where we have these one-dimensional channels encapsulated between 2 domain walls between an ABA and an ABC. So let's start with this. This is the boundary between an ABC and an ABA, and this we were able. We have different ways in order to actually estimate the strain just from looking on the atomic movement of the atoms from their equilibrium position. Here we can see that we have a shear strain. This boundary is along the zigzag, is along the armchair direction, and we can see that this row of atom actually across this boundary move to the row above, and this is exactly what we have when we have some shear strain, and this shear strain is effectively a vector field, a pseudomagnetic field, and then we will look on this structure that we have here. Here we have actually 2 one-dimensional channels the structure is the following. We have two one-dimensional ABC structures that are encapsulated between this domain well, and then the outer regions are the ABA region. And again, doing this analysis with the atomic position, we found that this is accompanied also by a strain perpendicular to this, a tensile strain perpendicular to these channels. And this tensile strain is effectively plays like a displacement field, and let's see how it affects the band structure. So let's start with the simple boundary. Here we have the ABC, the domain wall, and the ABA. And let's take some spectroscopy. This is the IDV as a function of location across this domain wall. We did it here in two locations. So this side is the ABC, where we see under minus 9.5 displacement field. So this is the ABC, where we see this sharp Van Hove singularity, the familiar spectrum. This is the ABA spectrum. And here in the middle, we see these in-gap states. We see this channel runs along this domain wall and is lying in the gap of the ABC and the ABA. Similar behavior we see here. And here we actually took a spatial mapping of the IDV just at the energy of this in-gap state, and we see this one-dimensional channel run along this boundary. And this is very similar to the domain wall between AB and BA. Here, actually, the valley Chern number flips by 2, and then we get the exact total of 8 channels. In the ABC, ABA, this is a little bit more tricky, because we have a change of valley Chern number across the boundary. However, the exact number requires more detailed calculation. Simple models shows a Chern number flip of 1. But what we can say that we have some topological state on the boundary. How many channels we cannot tell exactly at the moment, but this is what we see here at the boundary between the ABC and the ABA channel. And this is a simple calculation which shows the band inversion as we start from the ABA region close to the boundary, and then open a gap at the inverted gap at the ABA. And now let's look on this two-dimensional, one-dimensional, a pair of one-dimensional channels, and let's see how the strain affects the spectroscopy in this one-dimensional channel. So this is again the IDV as a function of gate voltage and as a function of energy, and let's compare it with the IDV that we know already from the two-dimensional ABC. So in the two-dimensional, we show that the application of displacement field opens a gap which becomes larger and larger, and we increase the displacement field. The Van Hove singularity also becomes more sharper, and we have this layer polarization. Now here we see that we don't see any layer polarization. This is the Van Hove singularity of the conduction, and this is the Van Hove singularity of the valence band. This is the topological channels. There is some region where the ABC is overlapping with this the dispersion of the domain wall. So this is the topological channel that I showed you before. And now we see that already at zero displacement field we have a large gap. So this we believe is induced by the tensile strain, which actually plays effectively as a displacement field and opens a large gap already at zero displacement field, and then the displacement field plays as very small perturbation, and indeed we see that the gap remains constant. So, and also we see that the Van Hove singularity already at zero displacement field becomes much sharper. So the effect of the tensor strain really opens a gap, makes very flat bands, and also kills this layer polarization. And the next thing, this is the last thing I just want to show, we wanted to see whether we see effects of correlation already without displacement field. And indeed, if you look at zero displacement field, we see already splitting of the band, which is also accompanied by some nematicity of the wave function. If we go to other energy, it looks more symmetry. So this happens at the splitting, but it turns out that this direction of the nematicity is correlated with the tensile strain, and this is also the center of mass of the wave function. We indeed see that around the Fermi energy already with no displacement field we see some effect of correlations. Again, this is a work in progress. We still need to understand the details and theoretically calculate the density of state. We have the profile of the strain and we want to calculate the exact band structure and the density of state with the application of strain and then compare it with our result and really get understanding of the effect of the strain in this one-dimensional channel and the effect of the dimensionality. That's it. So this is the summary without the strain, and thank you for listening.
Okay. We had discussion in the middle of your talk, but we still have time.
So, my question is that about this last part, you observe that there is a peak in for the 1D chain at zero energy, right?
At zero displacement field.
And zero displacement field at zero energy. Could that be related with this possible emergence of surface space that you're measuring when you look at this 1D chain instead of
The splitting that we see? How?
really TTOS peak? Zero energy.
So again, you're suggesting that?
I'm asking if that could be the emergence of surface states of the system at zero energy. That we mentioned.
What, the enhancement of the, so what is the effect of the surface states?
The zero energy TOS peak.
That the topological surface states, but we can recognize, as I showed you here, wait. Okay, so this is the Van Hove singularity of the conduction. This is the Van Hove singularity of the valence band, and this is the topological channel that we see on the boundary. We have a different, I didn't put it, but we have another measurement of the density of state which showed that there is an overlapping region of the domain wall and the one-dimensional when we can see both the Van Hove singularity of the conduction band and this topological, and we can see them both, so we recognize this.
Okay. Slide with conclusions. A simple question, both you and Aries with conclusions. Yeah. So there's IVC, stoner, and IVC. Both stoner and IVC can be charge or spin. It can be stoner ferromagnetism or valley polarization, and IVC can charge IVC and spin IVC.
Right, we cannot, I mean, we didn't do any spin polarized. In principle, we can, if we will do spin polarized STM, but at the moment, like, our conclusion is a combination of the theoretical calculation and the fact that we see the same order, but we cannot tell apart, but the fact that we didn't see a charge order there, we can't tell about the actual magnetic properties.
It's a different system. In Andreas' experiment, it's like a spin. This one is actually half metal spin polarized.
Even IVC is spin.
No, I was talking about the stoner.
No, stoner is spin polarized, but what about
the IVC
IVC?
doesn't know.
We cannot see superconducting because we don't go low enough in.
300
Yeah, this is the 300. Maybe soon we will have dilution-free STM, and then we are planning to put this sample in and really to correspond between the IVC and the superconductivity pockets. Yeah, this is another possibility.
If there are no more questions, thanks very much. What did you say in the 35 minutes? This is. What's this?